Now we want to analyze the randomized incremental construction of the vertical decomposition. So where do we stand? We're constructing the vertical decomposition, and we're at the same time constructing the search structure. The vertical decomposition does not depend on the order in which we insert the segment, so we can ignore that here. The search structure, however, and in this example we had that, very much depends on the order, or may very much depend on the order, and it may vary between linear and quadratic in terms of the size of the search structure. And what we want to show is that the expected size is actually linear. And the way we're going to show that is that we're going to analyze the expected number of nodes that we create in the ith step. And we're going to use a very nice analysis for this, which is called a backwards analysis. But instead of looking at the nodes of the search structure that are inserted, we're instead analyzing it in terms of the new trapezoids. And the reason that is a valid way of analyzing this is because the number of trapezoids that I'm removing and the number of trapezoids that I'm inserting, and in between the number of new nodes, all of that stands in a linear relationship to each other. So it's enough to count the number of, or analyze the expected number of newly created trapezoids, and we're going to use a backwards analysis for that. So what does backwards analysis mean? So first of all, I mean, if you think about how would you naturally analyze this, you would be looking at a search structure after I-1 insertions, all possible ith insertions, and you would have to do an analysis about segments that are not actually in the vertical decomposition yet. Backwards analysis does this in a very clever way, as in that you're looking at the vertical decomposition after the ith insertion. So all segments that we're going to talk about are already there. In this situation, if I think about the last insertion, every segment that is currently there has the same probability of having been the last segment to be inserted. So how can I analyze the number of trapezoids created in the last insertion? So I can look at all the segments that are currently there. I can count how many new trapezoids would they have created. So for instance, let's take one. This here, I can count 1, 2, 3, 4, 5, 6. So this one creates 6 trapezoids, or here we get a 9 trapezoids. I do this for every segment. And now the average of this, because every segment has the same probability of being the last, the average of this is the expected number of trapezoids created. So the quantity that we're going to analyze is the sum of all of these numbers. And then we can afterwards divide it by. So Ki will be the sum over all segments, and then the number of trapezoids that would have been created if this segment, so if the segment Sj, because the sum goes over J, if the segment Sj would have been the last. And now comes the main trick, and that is the following. So this sums over all segments and count trapezoids. But we can also look at this from the trapezoid perspective. So instead of summing over all segments and counting trapezoids, what we're going to do is we're going to sum over all trapezoids that are currently there and see how many segments would have resulted in creating this trapezoid last. The only segments that would have caused this trapezoid to be one of the trapezoids that were inserted in the last step, the only trapezoids are the ones that is either the top one. So let's say here this one is, it would have been this segment here, or the bottom one. Okay, the bottom one right now is a bounding box, or the one that gives me the left endpoint or the right endpoint. So only those 3 segments would have resulted in creating this one last. And if I do the same, let's say for this trapezoid, it's again bottom, top, left, right. And in this case, okay, bottom and top and right is the same, bottom and left is the same. But overall, it's at most 4 segments that would have resulted in any given trapezoid to be inserted in the last step. So if I now look at this sum again, so Ki is the sum over all possible segments, and then counting the number of trapezoids that would have been created if this segment would have been the last, I now rewrite this in terms of trapezoids. So I count over all trapezoids delta in the ith vertical decomposition. And now I count number of segments that would create that trapezoid, would create delta. Now I know these segments can only be bottom, top, left, right. So this can be at most 4. So what I get is the sum over trapezoids 4. So for each trapezoid I get at most a 4. So this is smaller equal. So this corresponds to 4 times number of trapezoids. So how many trapezoids do we have? We analyzed that previously. So if I have n segments, we said I have at most 3n plus 1 trapezoids. Or here, if I have I segments, I have at most 3i plus 1 trapezoids. So what I have here is I can bound this by 4 times 3i plus 1, which is 12i plus 4. So the sum ki is bounded by 12i plus 4. That was summing over all segments. So the average is bounded by 12i plus 4 divided by I, so roughly 12. Okay, so that's what we have so far. So what does that tell us? So we have that ki is bounded by 12i plus 4. This means that the average or the expected number of trapezoids created in the ith insertion, so ki corresponds to ki divided by I. So that is smaller equal 12i divided by I plus 4 divided by I. Let's say we're looking at the case I larger equal 4 to make our life easier. Then this is smaller equal 13i divided by I. So that is 13. So on average, we don't create more than 13 trapezoids. So that is in the ith insertion. So then I would be summing over all insertion steps. So from I is 1 to n. If on average I'm not creating more than 13 trapezoids, then overall I'm not creating more than 13n trapezoids in expectation. So the expected number of trapezoids created is indeed linear. So this is now about the size of the search structure. Now we are interested in the length of the search path, because the length of the search path corresponds to our query time. So let's say this is my query, this point Q, and I want to know how long the search path is. We can again use backwards analysis to analyze how long the search path might be. And for this we ask, let's say this is di, what is the probability that the search path got longer with the ith insertion, which means that from the I to di minus 1, the trapezoid in which Q lies actually changed. That again can only be if one of the defining segments was the one that was inserted in the ith insertion. So what is the probability that in the ith insertion one of these segments has been inserted? So I have n segments. These are 3. So the probability that one of these was the last is 3 divided by I, or because in general it could be 4 segments defining this trapezoid, I can bound the probability that the trapezoid in which Q lies in terms of the search structure after I steps, that is different after I minus 1 steps. I can bound that by 4 divided by I. So these 1, 2, 3, possibly a fourth one, divided by I. This means that the length of the search path, so what I'm analyzing, is the probability. So I'm looking at n insertions. The probability that the search path became longer with the ith insertion, that is bounded by, so I have the sum from 1 to n. The probability that this path got longer with ith insertion, with backwards analysis, we concluded this is bounded by 4 divided by I. So I have, this is 4 times this sum here. So ideally you recognize this sum already and know how large it is. To give you some intuition, I mean, the sum is somewhat similar. So we have 1 divided by I. So this is somewhat similar to the integral 1 divided by x dx, which is log x with a base e. To get a bound here, this is 4, can be bound by 4 times 1 plus this logarithm here, log of n base e. Here we were analyzing the expected length of the search path. This is bounded by order log n. Yeah, so the expected, that also means the expected query time is order log n. So where do we stand now? We have everything that we wanted to get given the assumptions that we made. So we given a planar subdivision defined by non-crossing line segments, so that's standard. We were assuming that all x coordinates are different. So let's keep that assumption in here because we haven't resolved that yet. So given the situation in the plane, we can pre-process the subdivision in order n log n time. So I didn't specifically discuss the running time now, but what we saw is that in each insertion, every time, in every step of the randomized incremental construction, we first have a search that takes order length of the search path, and we've seen that is order of log n or log I for the ith insertion, plus the order of number of new trapezoids, which is overall, if I sum over all linear. So what I get per insertion is essentially the expensive path is going down the search structure, the log n or log I, and then summing over all insertion steps. That gives us order n log n. We need order n log n to create this data structure. It has an expected linear size, and the expected query time is order log n. We have constructed the vertical decomposition for point location, but we haven't handled degenerate cases so far. So initially we made this assumption that we have a bounding rectangle. That's a valid assumption because for a given planar subdivision we can always find a bounding rectangle, but we also made the assumption that we have unique x coordinates. And if we wouldn't have unique x coordinates, then we would have difficulties deciding left, right for the same x coordinates. So how can we handle this degenerate case? The solution here is a shearing transform, and actually a symbolic shearing transform. So best to look at these pictures first. So essentially we are slightly, so if we have something vertical, we will slightly tilt it to the right so that these 2 points that were previously vertical, now this one is slightly to the right. We do this with this transform here. So depending on the y, we slightly tilt the x. We do it with a very small epsilon such that the overall x order remains the same. So what we want to have is that this point should still be before the next point in x order. We will actually not explicitly do this transformation. That's why it's called symbolic. But we will look at how would we need to do our computations if this transformation would have been done. So we're only applying it symbolically. Yeah? So we don't apply the transformation, but we use the algorithm as if it would have been applied. Specifically, what is the effect of such a transformation? It essentially just means that we're going to handle vertices lexicographically. So in lexicographical order. So in terms of the x, so the new x order is the old x order, just if they had same x coordinates, the one with the larger y coordinate will come slightly later. So it means we're going to use lexicographical ordering, but it also means that all of the point line incidences will still be maintained. So let's see how that affects the operations that we needed for the algorithm. So which operations did our algorithm actually need? So we had essentially 2 types of tests. We are testing for a given query point, whether it's to the left or the right of a vertical line, or actually more precisely left or right of the vertical line through some given point P. And we were testing whether Q is above or below a segment. Because we are using a lexicographical order, we will get that this test is executed. So if we do this test using the lexicographical order, we will have this test correct for the setting where we would have applied the shearing transform. Yeah, so test 1 will be correct, assuming the point that was sheared. if we use lexicographical ordering. Since we keep point line incidences, the above-below relation will also still be the same. So the second test will also be answered correctly. So this is all about degenerate cases. This solves what we had to solve for this algorithm. It's a very elegant way to handle these degenerate cases. So what we have is now the final theorem given a planar subdivision consisting of n non-crossing line segments in the plane, so we can pre-process them in order n log n time or expected time as to get a structure of expected linear size with expected query time order log n. So overall, what have we seen? We've been looking at the problem of point location as a data structure. We've seen a vertical decomposition together with a search structure. The technique that we were using was a randomized incremental construction, and we analyzed that randomized incremental construction using a backwards analysis, and that's all for today.